Hey team. You may remember on the first day of class, I asked each of you to tell why you decided to study science. Many of you talked about how you wanted to better understand the human mind, or said that you wanted to help people, or that you wanted to solve puzzles and figure things out. That is, that you wanted to do and apply science. I think students tend to start off with a lot of the right ideas about science. You make predictions ahead of time, you look for ways to prove yourself wrong, and you report everything you find. None of you said, I want to study science so I can regularly publish in high impact factor journals and get lots of big grant money. But over the course of the term, we've talked about the fact that the incentive structure of science pushes against methodological rigor and instead encourages cutting corners and moving fast and generating flashy and unexpected and, of course, statistically significant results. Although science is often described as being an objective enterprise, it's done by humans, and humans are influenced by their environment, pressures, and incentives. What this means is that the scientific method, the process by which we generate and test and report our findings, is not immune to all of the things that humans can engage in, like bias and hype and distortion. So over the course of the term, we've talked about what can go wrong at each step in this process. We've talked about how a lack of replications makes it difficult to refine hypotheses, how low statistical power increases the rates of false positives and spurious results, how poor quality control and lack of construct validation clouds the data that we collect, how p-hacking and harking interfere with our ability to interpret data, and how publication bias prevents the scientific community from seeing some or maybe even a lot of the scientific work that is conducted. So it's not all doom and gloom. I'm not going to leave you with this, but where do we go from here? How do we fix it? One of the themes that has emerged in this course is the importance of transparency in the scientific process. This is, in fact, another place where early scientific training tends to get it right. You need to show your work. Or put fancier and in Latin, you should have to take nobody's word for it. We should be able to check on others' work in order to verify it. Now, typically, scientists do all of this work in private, out of the view of the rest of the scientific community. So all we actually see is the paper that's published, but not all of the decisions that were made along the way, not the data, not how and when the hypotheses were generated, etc. But increasing the transparency of this process has the potential to deter or at least identify these questionable research practices and other impediments to science. So the first place we can shed additional light is making it clear exactly what we did. By sharing study materials, researchers can help to ensure that future researchers can replicate their work and understand their work, right? You can't assess the construct validity of a scale if you don't have the scale. We can also share data and code in order to help reveal and deter p-hacking because it becomes more apparent if you tried lots of analyses and didn't report them all. It also helps others understand what you did, helps facilitate future meta-analyses and reanalysis of the existing data. Pre-registration helps to reduce p-hacking and harking and other sources of bias because it forces researchers to call their shots ahead of time and therefore more clearly delineate confirmatory analyses from exploratory ones. So there's a lot to gain from transparency and at relatively low cost. But transparency is not enough to fix all of the problems that led to the replication crisis. You can pre-register a poorly designed study. You can share data that's been analyzed incorrectly. That something has been pre-registered doesn't mean it's good. It means it's easier for you to evaluate whether or not it's good. Put another way, transparency does not guarantee credibility. Transparency guarantees we get the credibility we deserve. So transparency is important because it enables people to evaluate the quality of the work. But it's not enough. One reason that it isn't enough is that you can run a really great, totally transparent and wholly open study that renders null effects and not be able to get it published. So one of the really exciting innovations of the last decade is the advent of registered reports. And as you read, in addition to dealing with the issues that pre-registration solves, registered reports also protect against publication bias because decisions about publication are made prior to seeing the results. Registered reports can also help to improve the overall quality of the work because they are peer-reviewed prior to completion. Another way we can try to counteract some of the problems associated with the replication crisis is by doing team science, that is, conducting research as collaborations between multiple laboratories. This can help to ensure greater statistical power and make our research less homogeneous and weird. There are also new initiatives to encourage replications. These help to make replication part of mainstream teaching and corroborate prior findings. And there's just one other really important thing that we need to do to help reduce the issues that led to the replication crisis. You know what it is? You want to guess? We need to train the next generation of scientists and consumers of science. So I'm looking at you, Psych 399, about the importance of rigorous and transparent science. There are courses like this that are happening all over the country and the world. And there are organizations and initiatives intended to help make it easier for others to learn and teach about these issues. Here's what I want to leave you with. John Maddox, who served as the editor of the journal Nature for decades, was once asked by an interviewer, "How much of what you print is wrong?" To which Maddox responded, "All of it. That's what science is. New knowledge constantly arriving to correct the old." Now, my guess is that Maddox meant this about content, right? About like the facts of science. But it's also true of the process of science as well. We're constantly learning new things about how to do science better and how to make our work more transparent, more robust, more equitable, and more credible. My now pre-registered prediction is that in 30 years, in 50 years, when people are looking back at the history of psychology, they are going to point to right now. They're going to point to this credibility revolution as the time in which things changed for science and for our discipline. That the initiatives and the methods that we've talked about this term are what changed psychology from being just incredible to being truly credible. This is our opportunity to change our behavior in a way that will ultimately strengthen the practice of science. All right, in the last couple of minutes I have you in this class, I want to emphasize something really important. All of the initiatives that we've talked about, all the new platforms and the organizations and the tools and the methods, these are all just ideas that people have had to try and improve a system that they care about. So registered reports and journal badges and the open science framework, all of it, these are not things that randomly and spontaneously just magically happen. These are things that happened because some scientists were frustrated about the state of our field and spent the time and energy to figure out how to make it better. So the next time you are frustrated at the state of science, I would encourage you to not despair and give up, but to follow their lead. Science is only going to improve if we improve it. So keep asking, how can we do this better? You've been a wonderful class, and it has been a pleasure to work with you. Good luck with the rest of your work, and be in touch.